All right, so the very first activity at the top of this page is talking about mathematical modeling something. That's what we just did, where you guys were describing transformations to the rest of the people in your group. Now, the word transformation, we talked about this last week. It does have a specific meaning. We talked about it in terms of functions, saying that it's a one-to-one function on the plane. And the main takeaway there is that if we start with a triangle, we're going to end with a triangle. If we start with a quadrilateral, we're going to end with a quadrilateral. A transformation doesn't mean it has to look exactly the same in the end. It just has to be the same type of polygon. Okay, so we do have another subset of transformations that we call, well, let's talk about it right here. So the very first blank in this page. Transformations that preserve lengths of segments and measures of angles are called rigid transformations. It's going to be hard to fit that in there, but you can do it. Rigid transformations. And I'm going to go ahead and highlight that sentence as well, so when you're done writing, you can underline the sentence or something like that. Practice. But if you need to, you can just write in the margin and draw an arrow to the blank if you need to. All right, so the rigid transformations are the reflections, rotations, and translations. And like I've already said, that's really what we're going to focus on. So if you know those three, then you're good with the idea of transformations for our purposes. But later in the year, we're going to look at another type of transformation called a dilation. Can anyone remind us what a dilation is? Bigger, smaller. So you're taking an object and you're going to make it bigger or smaller. And we'll talk about the actual process for doing that when we get to that point, but that won't be till like halfway through the year. So in the meantime, we'll just not worry about that. But a dilation is an example that preserves angle measures, but not the lengths of the segments. So we're only going to work with rigid transformations. And this is something we've already talked about, but we'll reiterate it here. A figure that is about to undergo a transformation is the preimage. And the figure that has undergone the transformation is the image.
Does that say angle?
Yeah, angle. So then we've got preimage and image. Those are the only blanks you have to fill in. I'm going to turn this display down here into a table. And on the left side every time we've got our preimage. And on the right side we've got our image. Alright. So moving forward, we're going to take time with each one of these transformations. So we'll talk about translations on their own at first, and then reflections, and then rotations. And then after that, then we'll put it all together. So today we're introducing all this stuff, but you don't have to worry about needing to know everything about these transformations right now. All right. So what we're going to do real quick is we're going to look at this page right here. And I'm going to get to a blank screen here in just a second. But think about, first of all, a rotation. So let me get to this. So if I tell you guys to do a rotation, what are some things that we need? What's information you need to know? The preimage. Okay. So now I tell you, rotate this preimage. Most of the time we're going to be working with triangles, sometimes quadrilaterals. So I'll just keep using triangles for our examples. So here's your preimage. I'll call it ABC. And rotate that. What else do you need to know? The direction. So we might consider that the angle of rotation. So I tell you to rotate this 90 degrees. All right. So is that everything you need to know? What else do you need? Which There you go, the direction. Okay, so I tell you 90 degrees. Okay, I didn't hear. So now we've got the direction, and let's say I tell you to go 90 degrees counterclockwise. Okay, so you're pretty well set up. Do you have all the information you need, though? What else do you need to know?
Are we supposed to write this on the line?
We're going to write it on the line in just a second. We're just kind of working through the logic of it real quick. No? Say that again. The point. We need to know what are we actually rotating from? Rotating around which point? Okay? So we need to have a point that we rotate around. So I will go ahead and give you this point right here. You don't have to actually have this written down, just as long as you're following along. And I'll just call that point X. All right, so now I'm telling you rotate triangle ABC 90 degrees counterclockwise around point X. Sometimes you'll hear rotate about point X. So either way, I mean, it's pretty intuitive what they're referring to. So now we can go ahead and do that 90-degree rotation, and we would end up with something that looks roughly like this when we're done. All right, so let me just label it real quick. A prime, B prime, C prime. Oh, I flipped that around. B prime, C prime. There you are. So that's what it would look like after the rotation. That'd be about 90 degrees. And like I said, we're going to spend time looking at rotation specifically. So not a big deal right now as long as you understand the basic idea. So let's write those things down. Here's the actual information that we need. We need to know, first of all, the preimage. Secondly, we need to know the degrees of rotation. Next, we need to know the direction of rotation. And in parentheses here, I'm just going to put clockwise or counterclockwise. And I just abbreviated that. If you need to write out what that means, please do. We're going to develop this further later, and we'll talk about positive and negative rotations, which is just another way of talking about clockwise and counterclockwise. But anyways, we need to know the direction. And then the last thing we need to know is the center of rotation. We can call it the point of rotation, but the name that we typically use is center of rotation. And with that much information, we now can actually rotate any preimage that we're given. Okay, does that make sense? Okay, so now let's move on and look at a reflection. So, for reflection, what do we need? We need a preimage. I'll just draw another similar triangle to that. All right, so there's my preimage, and what else do I need? Remember, this is a reflection. A mirror?
Like your point of reflection?
Kind of. We do have things called points of reflection, but that's reflecting through a point is a little different. We're not going to be doing that really. And that's actually just another way of talking about dilations and rotations. So instead of a point of reflection, what do we need? A line of reflection. All right, so I give you this line right here. And I tell you to reflect over that line. Do you need any other information? No. You're good to go with that much information. So if I draw the image of this somewhere over here, just guessing, doesn't matter, then we really have all the information we need. Okay, so the reflection is going to be the most straightforward. And all we need is the pre-image and the line of reflection. Okay, easy enough. Last one to talk about, we have the translation. So if I've got a translation I want you to do, what information do you need to know? Okay, we got that, the pre-image. Now it's this triangle right here. Translate that triangle. What do you need to know?
Where are you going to put it?
Okay. All right, Manuel, I'll go ahead and take that. All right, we need to know where it's going to go, but how are we going to know where it's going to go? Well, you can do a translation to a point, but the way that we typically do it is a slightly different way. Okay, it is possible for me to say, here is the point where this should end up at, and that's fine, but let's say I don't give you a point. What do you need to know instead? Say that. Angle? So another way of saying that is the direction that we should translate this. So we need to know a direction. Let's say just for simplicity's sake right now, let's say I tell you to go down. And now what do you need to know? How far? So now let's say I go down, distance. There we go. So the direction and the distance. So we need to go down, I'll just say 5 inches. And right now, we can just come up with our own scale. Let's say this is 5 inches right here. All right? Doesn't look very good, but I translated this thing down 5 inches. All right? So now we can go ahead and write that down. We need to know the pre-image, of course. We need to know the direction of translation. And we need to know the distance of translation. Direction and distance. We combine these two together, direction and distance, into what we call a translation vector. So let me kind of combine both of those together, because sometimes you'll hear about, like, here's your translation vector, and go ahead and do the translation. We're not doing stuff like that as much in our class, but you might see examples of it. And so, for the translation vector, it's really important to understand, I'll give you guys a second to write all that down, but it is important to understand that even though it looks like a ray, it contains very specific information in it. Has everyone got that written down? Okay, so let's go back and look at this for a second. I want to expand on translation vectors for just a minute. So let's say that you have the same pre-image here, but I give you a translation vector that looks like this. Then what that is telling us, as long as you know it's a translation vector, this is not a ray shooting off toward infinity. This is telling you exactly the direction that you should be translating, meaning you want to go from left to right here, and you want to make sure that you're going that distance that's given. Whatever that distance turns out to be on paper, that's how far you'd want to go. So I want to make sure this goes over the same distance. Now the translation vector does not have to be connected, so the translation vector being there or right here doesn't matter. As long as it's the same information, I can move that translation vector around. So that gives me my image somewhere about right here. I'm not drawing things very well today. But anyways, there's the image about right there following that translation vector. And the reason I wanted to expand on the vector for a second is because this is an idea that comes up in other fields. Specifically, I'm thinking about physics. So the vector having both distance and direction, they'll talk about that as magnitude and direction in other fields in physics. So that tells us a lot of things, and it's really useful for modeling forces. So there will be a lot of you who end up taking a physics class one day. So now imagine that you've got a situation where there's maybe a ramp. And I know this is like a very brief kind of physics lesson. This isn't a physics class. But it's just showing the usefulness of vectors. Now you've got a ball rolling down this ramp. It's going to be, there's a lot of forces at play when you look at this. And rather than trying to imagine this with the entire ball and that ramp completely, we can just model this with arrows. So we're always going to have some kind of force of gravity. You're going to have a little bit of a force of friction that pulls this thing back, slows it down. But that's not going to be nearly as much as the force that's dragging it forward. Oops, I can't. That's not what I wanted. All right. So you're going to have all kinds of different things. You have something called the normal force, which is kind of pushing back on it. So you take all these vectors, and that models what's happening to this ball. And the combination of the vectors reveals kind of where the forces are going. And it's a really useful concept. And the length of the arrows you draw show the force, the magnitude of the force. Okay? So you can even do things like this later, where you've got a vector moving one direction, a vector moving another direction, and you can just kind of combine those vectors together and figure out what this vector is that goes from the very beginning to the very end. So incredibly useful concept, and I think it's worthwhile just talking about vectors for a minute. For our purposes, it's only for translations, but you will come across this stuff later and find them very useful for modeling. All right, so that's as much as we're going to be covering today. We're going to look at the backside of that tomorrow, so make sure you bring this back to class.